This is Unit 5, Lesson 3, Part 1, the first derivative test and how we can tell whether functions are increasing and decreasing. So the first topic we're going to cover is how to determine intervals on which a function is increasing or decreasing. So what we can do is we can use the derivative to classify our relative extrema as minimums or maximums. In the earlier part of this unit, we were using the critical numbers to determine whether we had relative mins or maxes. And now we can actually use a first derivative test to find where they actually occur, whether it is a min or a max without using the graph. So how we're going to go through this is we're going to use a red pencil and we're going to circle all the points that correspond to a local maxima of f. And we are not including the endpoints. So we have two local maxima. We have one here at A, and we have one again here at D. Now we're supposed to state the x where they occur, so we have one at x equals A and one at x equals D. The next thing we're supposed to do is talk about how f is changing. So f is changing from both of these, from increasing to decreasing. So even here, it's increasing and then it's decreasing. So f changes from increasing to decreasing. Next part, at each maximum value, f prime changes from positive to negative, because since we're increasing, the slope of that tangent line will be positive on the way up, and it'll be negative on the way down. So from positive to negative. Part D, there isn't a part D, we're going to number 2. Number 2 now says, use a blue colored pencil, circle all the points corresponding to the local minima of f. Do not include the endpoints. And we're going to do the same kind of thing. So let's look at the graph first, then we'll fill out the answers here. Okay, so using blue, let me use a different shade of blue since I use this blue all the time for writing. I'll use a light blue. Okay, so we have one spot, and that's here, whoops, at x equals c, where we have a local minima. And what's happening to f? Well, f is changing from it's decreasing here, and then after the minimum, it'll be increasing. And then we are to add what the f prime changes are. And since we're decreasing, the slope of the tangent line here will be negative, and on the other side of the minimum, it'll be positive. So those will be my answers for number 2. So state the values where it happens. It happens at x equals c, and our f is changing from, it's decreasing before you get to c and increasing after c. At f prime, since it was decreasing, will have a negative slope, and after you reach c, it changes directions. It'll have a positive slope. Okay, so at each relative or local extrema value, f prime of x, the derivative of f, is either 0 or undefined. And let's take a look at the graph again. So looking at our graph, what we can see is at the first red point at A, we can draw a horizontal tangent line there. We can draw a horizontal tangent line, so we have an m of 0. Same with here at C, we have an m of 0. But here, m is undefined. F prime does not exist, because we have a corner or a cusp. Okay, so that's what we have so far. Now going to the next page, we're supposed to use a green pencil and sketch the tangent line at the following points. at point B. So let's use green here. And let me erase some of this blue I have here in between. We don't really need the blue. Okay. All right, so we're using green and we're supposed to draw a tangent line at point B. So here's B, here's my tangent line at B. And also at point E, we're supposed to draw a tangent line, which is also horizontal, and at point D, which we cannot draw. We already talked about that. Okay, so now we can answer the questions for this section then. Okay, so at point B, f prime of B is negative. Just to double check, you can see that the tangent line we drew there has a negative slope. So f prime of B is negative. Describe the change in behavior of the graph of f at this value. F changes from concave down to concave up. And let's look at the graph real quick so we can verify that. So what we see happening here is before we get to point B, this curve has a maximum, so it's sloped down. And then right at B, it changes, and now it's starting to be the beginning of the slope up to the minimum here like that. So it's switching from concave down to concave up. Okay, so that's what's happening at B. Okay, so at point D, what we see here is we kind of have the cusp. So at point D, D prime, f prime of D is undefined, because that's our cusp. Describe the change in the behavior. So f changes from an increasing to decreasing, because up to D it's increasing, and right after D the graph begins to decrease. At point E, f prime of E is 0. If you recall, that's where I said there was a flat spot there, so we can see that f prime of E here is horizontal, so the slope will be 0. Describe the change in behavior at F. So again, we're changing from concave up to concave down. We're changing our concavity. So F changes from concave up to concave down. All right, we'll take a look at the graph of that again in a second. So looking at the graph, we can see that before we have a concave up situation here, right along here, and then once we get to E, all of a sudden the graph is flipping over and switching to a concave down situation there. Okay, so of these 3 points, which 2 of the points are inflection? And that would be where we change our concavity. So that was at x equals b and x equals e. If a function f has a relative extreme at a point, then the derivative of that point is either 0 or undefined. Is the converse of the statement also true? So the question is, if the derivative is undefined or 0, does that automatically mean that we have a relative extrema? And the answer to that is, of course, no. What point justifies this answer? And that would be E, because f prime of E is equal to 0, but not a relative extrema. It is a change in concavity, but not in terms of a maximum or minimum. So you have to be careful with that. The converse of that statement is not true. We can use the zeros and undefined values of the derivative to find our extrema, but that doesn't automatically mean if we have zeros and undefined values that they are extrema. Okay, so here are some definitions. A function f is increasing on an interval if for any two numbers x1 and x2 in the interval, and x1 is less than x2, this implies that f of x1 is less than f of x2. Okay, so simply speaking, what we have here is any graph we have. If we have an x1 here, and we have an f of x1, and then we have an x2, and then we have an f of x2, and if x1 is less than x2 and f of x1 is less than f of x2, then we can say that the function is increasing on that interval. Now, we can also say the same thing going the other direction. So if we have a graph, and here's my x1, and here's my x2, so here's my f of x1, and here's my f of x2. What I can see is, and this is a typo there, that should be for x1 less than x2. We know the interval is decreasing if f of x1 is greater than f of x2. So we can see that as we move along here, our y values are decreasing. Okay, so let's do example 2, and we'll finish up this video, and I'll continue in video 2. So example 2 says, the graph of y equals f of x is shown at right, and is defined from -3 to 7, including the endpoints. We're to list the open intervals over which the function is increasing, decreasing, or constant. So we can see that the function is increasing right here. This is the only part of the graph where it's increasing. So it's increasing from -3 to -1. Here we have an x of -3, and here we have an x of -1. Okay, next section. It is decreasing from 2 all the way down to the end at 7. So we have an x value here of 2, and we have another one at 7. And everywhere in between there, it is decreasing. So it's decreasing from 2 to 7. And finally, where is it constant? It is constant from -1. I don't like the color, it's too close to the other one. It is constant from -1 to 2, because we have no change in y value. So it is constant. It is constant from -1 to 2. Little note here, a function is said to be monotonic on an interval if its first derivative, and which does not need to be continuous, does not change sign, which means it has the same direction through the entire interval. That's what monotonic means. Okay, so we'll stop here, and I'll finish in the next video.